Okay, so now we have um, our pin set up as an input, as an output pin. We've specified where it is on the chip. Now we have to do what's called generate an API. I mean, I could start writing code here, but the problem is if I start writing code is I don't have the API generated just yet. So there's all those pre-built-in functions, and what I mean by that, um, if I go to the data sheet again, all these pre-built functions in the application program interface, we don't have access yet to because I haven't built the API. So remember, first thing, once you create it, you're going to have to put in all of your components from the catalog, assign any of them to the pins that you need, then we're going to generate the program application interface. And it's this little here, generate application. It's right next to the little chip looking thing and also next to this bug, which actually is for debug. So we're going to generate the application. And so this is not programming the chip or anything. This is just generating the application. And I will tell you right now that if you're trying to run your programs off the USB drive, you're going to be limited off the speed of the USB drive. I like to do all of mine on the on a hard drive, and then if I need to, I'll transport them onto a USB or a cloud drive. Now you can see what's happened here. All this generated source code, it has now just written all of this code for us. And all of this code is going to be something that we can use and would be helpful for us. Specifically, let's look in here under BLED. Now this should be familiar to some of you as far as header and C files, but if I look in the BLED header file, there's a lot of different, there's structures, there's all sorts of other different thing here as far as like, well, here we can even see some function prototypes for the BLED read, the BLED write, so on. And so this creates a bunch of stuff for the header file. And then if you go in here under the C file, you can actually find the code for the BLED write. For instance, here is the code for the function BLED underscore write. So we're not going to go into what all this is because then there's another thing that's okay, BLE underscore drive, and then you're ANDing it with a mask here, and this is all having to do with bit shifting to make sure that you're getting to the correct pin and port. The good thing is that this software program does this all for us by hand. Back in the older days, not trying to say I'm old, we actually used to have to do this all by hand. We'd have to just recreate this. And so what we'd of course do is we'd create it once and then we'd have these libraries that were pre-built at a company. And so we really quickly said, okay, well, we need to just have these libraries and all these stuff pre-built. And so that's kind of why we've gotten to this. And now a lot of companies just have it so that the software packages basically pre-build all the APIs for commonly used components. Now they won't pre-build all APIs that you would ever need, but for most of your applications, especially with what we're doing, you'll have here. So now if I go to the main.c here, I just double clicked on it, we can see here that it kind of creates here a template here. We should always, of course, change some of this stuff, you know, copyright your company, blah, blah, blah. What I want at least here is, you know, put your name up here, and then, you know, the assignment. Assignment number, and then problem number, because some assignments will have more than one problem. Okay, so that's what you should be including in the top there. And then this CY global enable, that enables the global interrupts, and there's a little comment there. This line of code, you should never change. Never change this line of code. It just enables all of our global interrupts. Now this is where we place our initialization or startup code here, which we don't really have any currently. When we get into some other more advanced applications, we'll have some startup code. And then notice here, we talked about this in the other video, I have this infinite for loop, and it says place your application code here. So this is where we're going to place the application that we're trying to run. And remember, my goal was to make the blue LED blink. Okay, well, one thing here, and we're going to do this kind of the what I would say is not the best way, and then we're going to look at an example and do it two more ways, both of which are, I would say, better. Okay, so place your code here. So first off, there's we don't really have to do much here. We have to do bled write, and if you start typing something in here, I'll start typing bled underscore write because I'm trying to write to the pin. You notice how it has you can do control space to show only macros, but if you hit tab, it auto completes it. And then it also gives us help saying, hey, you need to put in some kind of int value here. And so we're going to either put in a 0 or a 1. Now this is what is a little bit different than what you probably are thinking of, is this actually turns the LED on. And this has to do with how the LED is connected up to the chip. So the way the LED is connected up to the chip is you have power connected to a resistor. Actually, the resistor is actually power connected to the diode LED connected to a resistor, current limiting resistor, connected to the pin. That's how this is connected up. How do I know that? Well, you have to just look up in the user manual. But that is actually the way we should connect LEDs up in general. And the reason is that the reason you don't connect it up the other way is that often these microprocessors can't output enough current to drive an LED. They can sink enough current, meaning that it can take the current in through the pin and sink it to ground with no problem, and it can take that current, but it can't actually output the current. So by connecting it this way, we're basically, when we put a 0 on, we're sinking that diode to ground, and so you got power on one side of the diode, ground on the other side, and so we know the diode's going to turn on. Okay, so that's how we have it here. So it's a little bit opposite what you think, is you'd write a 0 to turn the LED on. And then we have to, if we're going to create it to delay, we're going to have to delay a few seconds or so in order for it to be on so that we can see it. Because if I were to turn it off right now, then it's going to be on and off so fast that our eyes won't be able to catch it. It's either going to always be on or always be off, because we'll be running at the speed of the clock of the microprocessor. So we'll be turning things on and off essentially roughly at 42 megahertz, or 42, I can't remember, I think it's 42 megahertz, but it wouldn't be exactly that because, you know, there's several lines of code that have to be executed. In any case, what we're going to do here is we're going to put in a delay here. And CY delay is the most common we'll use. And notice it says here it needs an unsigned integer 32. I could look up what this is, but it says milliseconds. Oh, well, okay. I'm going to just delay 100 milliseconds. And then I'll do bled write, not wake up, write. Then I'll turn it on, turn on LED, delay 100 milliseconds. And then I'm actually going to delay again. And some of you might be saying, hey, you forgot a semicolon. And actually, that's what's nice, is this programming language helps us remember, or the, not the language, the interface helps us remember that we forgot to do that. So, okay, bled write, and so that's turn on the LED now. All right, so I got the LED turned on, then I turned it off, and I'm delaying 100 milliseconds in between. And now this is a for loop, so it's just going to repeat this infinitely. So it's just going to keep executing this over and over and over again. So I don't have to do anything else. And so at this point, what I'll do is I will go ahead and program my chip. Now, this time it's going to go through, and you can see that it's compiling everything, and then there was that little green line there that showed, and then it will be programmed in, and then mine is flashing, And it's flashing at a frequency. Well, if we think about this, what is the frequency that's flashing at? Well, let's think about this for a second here. One period of this would be 200 milliseconds because it's on for 100 milliseconds and then it's off for 100 milliseconds. So one period would be 200 milliseconds. So the frequency would be 1 divided by 200 milliseconds, which is 5 hertz, which, you can see basically that means it's going to be blinking 5 times per second. And, that looks like it's what it's roughly doing, at least at my computer here when I've connected up. So very basic program, nothing very exciting going on with that. All right, so let's do another. We're going to do the exact same thing, but we're going to do it in a slightly better way here. In fact, actually, instead of doing the slightly better way, we'll a new program for it. We'll just modify this one. Because there's a problem with this here, the way we've written it here, is that we have this BLED write, and we have to remember, we always have to remember that 0 is off and 1 is on. But just reading this code, if I see BLED write 0, doesn't make a lot of sense to me. And if I even look at the program application interface, and look at the way they do it, they here have a pound define LED on and a pound define LED off. So we could go ahead and do that here. In fact, we might even have those. Do we? No. So what we're going to do here is up ahead of our program is what we're going to do is called a pound define. And this is going to be LED on, and I know they do the U. I always do 0x00 is the way I do it, and for hexadecimal format. And then I'm going to do a pound defined LED off 0x01. Now, let me move my screen here a little bit. This Code Explorer probably is something that you have already here. These are what are called macros, these pound defines here. And what's important about a macro is, while it looks like it's a variable, it's really not a variable in the sense of that you're programming this variable into the microprocessor. Basically, it's kind of our own little variable for this page of code. So that instead of writing 0 here, and you might say, well, hey, I have to type more things. Well, but you can still autocomplete, but I'm going to do LED on and then LED off. And you might say, well, why do I do this? Well, clearly, as far as readability of this code, reading this here is much clearer that, oh, well, be LED right? Well, of course it's turning the LED on. In fact, I could probably get rid of this comment now because, well, it's clearly turning the LED on. And we could even get rid of maybe some of these comments here, turning off the LED. And then I'll just have one comment at the beginning of this code here and says, makes blue LED blink at 5 hertz. That's it. So instead of having a line of code for a comment for each line of code, I can do that. And now, the reason I can get away with that again is that this has this nice little LED on and off. Now, one thing I want to emphasize here is that notice that when I hover over this macro, it actually has 0x00. When this is compiled, and I'll compile it right now just again, even though nothing's really changed, what's happening is it's actually not putting this variable LED on or LED off into the chip. What it's doing is, when it's compiling, is the first step in compiling is basically saying everywhere it sees an LED on, it's going to put the number 0 in there. And everywhere it sees LED off, it's going to put the number 1 in there. And so that's really what it's doing, is that every single time it sees that, it first does that, then it goes through and programs. But these macros make it so that our code is much easier to read. And I'm going to be requiring that you not only comment your code, but that you use macros as well. Now, there is another way that we could do this. I'm going to start a new project. And now I'm going to do target device, last used, empty schematic, add to current workspace. See, instead of creating a new workspace, I'm going to add to the current workspace, and I'm going to call this blink 2. Now, notice here we have, and this is where you have to be careful, we have a project 1 here now, that if I hit this plus, this is what we just wrote, all of this stuff here. This is our first project, all of our code there. And then we have a project, oh, I spelled blink wrong, blinic 2, and it's in bold. Well, that's important because that bold means that that is the active project. Meaning if I were to hit program right now, I'll just go ahead and do that. It's generating source and everything for us. If I program it, nothing, the LED blink should turn off. And it shouldn't be doing anything because, well, I haven't done anything in this program yet. I haven't created anything yet. So of course it's doing nothing. If you wanted to program blink 1 though, you would have to set that as the active project, then click on the program button again, and it will program that one in. Now it doesn't recompile it because it's saying, hey, I don't need to recompile the code, but it will program it. So you need to make sure you know which one is your active project. The other thing I like to do is make sure, like when I'm in a new top design here, I say, okay, close all but this. And you can even double click so that I don't have a bunch of other windows open. All right, so with this one, let's go ahead, we'll do a digital, instead of, you can also just search for pin, and you can say, okay, digital output pin. And this time, let's do the green LED. Strong drive, no hardware connection. So initial state here is low. So if I click on OK, that means the initial state of this is that it's turned on. So if I go to the pins here and then assign this, if you look on your chip, this should be port 0, pin 2. I put it on the wrong pin there for a second. Port 0, pin 2 for the green LED. Now if I don't even write any code here and I program it, first off it's going to generate the APIs for us. But it should come and the green LED should just be on solid. And that's again because the initial state is low, which we know that means the LED will be on. But if I change the initial state to high and then just reprogram it, the LED will be off. Now that's just important. It's not that critical with an LED, of course, but it is critical in the sense you need to know what your initial states are. Initial states are always critical to know. So that's just knowing what our initial states are. All right, so we'll just leave it like that for now. What I want to show you is that there's often more than one way to do programs here. So I'm going to, instead of changing all this here, we're just going to go right to here. And I'm going to have it blink at 5 hertz. And what I'm going to do here is I'm going to just simply do, I'm going to do one line of code here that's going to toggle. So I'm going to do GLED write, because I want to write to it. But then instead of putting 0 or 1 there, I'm going to do a GLERD read. And then what am I going to do here is I'm going to put a not in front of it. Because remember, the exclamation point is a not. Now, what this does here, this is first going to read the current state of the LED. So it's going to return either a 1 or a 0. This right here is going to return a 1 or a 0. Then the exclamation point is going to invert that. It's a not statement. So if it reads a 0, the not's going to then make it a 1. So then, the current state of the LED would be 0, but then it would be writing a 1. So it's going to write the opposite state of it. So this really is a toggling method. And then we still have to put our delay in here to make sure we have a delay. And since we're doing 5 Hertz still again, it would be a delay of 100 milliseconds. And then if we program here, we can see that it's blinking again. Now it's just the green LED that's blinking. So there's more than one way to program these things.